Radiation, we just have to talk a little tiny bit about radiation here so that we can understand a couple of things. A guy named Ernest Rutherford studied radioactivity. The really kind of sad thing about these early researchers into radioactivity is they didn't understand how dangerous it is to you physically, so many of them died prematurely because they were playing with dangerous things that they didn't know were dangerous, right? There are 3 types of radiation: alpha, beta, and gamma. And those are the Greek letters A, B, and C. Alpha rays are helium atoms that are stripped of their electrons, so those are helium nuclei. Beta rays are beams of electrons, and gamma rays are really high energy electromagnetic radiation. And so I'm just kind of telling you about those so that if we use those terms, you at least just have a general idea. So Rutherford's student did an experiment at his suggestion where he fired alpha particles. So he had this generator that made alpha particles. That's a helium nucleus. He directed this beam of alpha particles at a very thin piece of gold foil. And they were trying to test this plum pudding model of the atom and see if that was correct. And so what they thought would happen is that the particles would go straight through the foil. This is a circular fluorescent screen that allows them to detect these particles. When a particle hits it, there's this little tiny glow of light. And if you have a lot of particles going through here, you can see a glow where the particles are hitting mostly. So what they found is that most of the particles did go through undeflected. They're like, yeah, that's what we expect. Some of them were scattered, but what was really shocking is that some of them were deflected backwards. They bounced off this piece of foil. And what Rutherford said about this was, he said it was as surprising as if you fired a 15-inch shell, a 15-inch shell, that's like a cannonball, at a piece of tissue paper, and it bounced back and hit you in the face. That would be surprising, wouldn't it? You don't expect a piece of tissue paper to be able to deflect a 15-inch shell or a 15-inch cannonball. So this was very shocking to them because they thought the plum pudding model was correct. So what do? This is evidence that there's something wrong with the plum pudding model. And so they try to explain what's going on. And so that's what he did. So here's the plum pudding model with these little tiny electrons, and they would expect the alpha particles to go straight through. They did not. What they found as an explanation was, well, what if all that positive charge is all clustered together in a nucleus, and that would explain how most of the particles went straight through, but every once in a while, one of those particles would hit this and bounce back. This is very, very dense, and so if a particle makes a direct or close to direct hit, it's going to bounce back. You can kind of think of it as shooting airsoft pellets at a volleyball net, perhaps. Okay? Most of the airsoft pellets are going to go through those big holes in the volleyball net, right? But if one hits the string, it's not going to go through. So there's this little bit in here that if the particle hits, it's going to bounce back, but most of them are going to go straight through. So that led to Rutherford proposing a new model of the atom, a nuclear model. So in this model, we have negatively charged electrons that are distributed, so they're still, kind of zinging around out here, but they're distributed around a positively charged nucleus. So instead of this being a cloud of positive charge, all the positive charge is concentrated in the nucleus. And so the atom itself has a diameter of about 10 to the minus 8 centimeters. So that's 10 to the minus 8 centimeters. And then the nucleus itself is much, much smaller, about 10 to the minus 13 centimeters. So that's a big, big difference. We've got protons and another particle called neutrons that we haven't talked about. Those are all in the nucleus, and the electrons are going around the outside. Based on the heaviness of the nucleus, Rutherford predicted that there must be something else in there. They knew about protons and they knew about electrons, but those did not explain their observations about atoms. So he predicted there must be some other particle in that nucleus. And about 30 years later, neutrons were discovered. And they're given the symbol N with a 0. The neutron is about the size of a proton, but it doesn't have any charge. Now this table here is something that you do need to know. There are 3 subatomic particles, electrons, protons, and neutrons. These are their symbols. You need to know where they are located. The electrons are outside of the nucleus. The protons and neutrons are inside the nucleus. Relative charges are very important. The electron is negative. The proton is positive. The neutron is neutral. So proton and neutron should be easy to remember. Proton is positive. They both start with P. Neutron is neutral. They both start with mu, right? And that leaves the electron to be the other guy. He's the negative one. Relative masses, the proton and the neutron are roughly the same size. So we say that they're essentially the same size. The electron is 1,836 times smaller than those. I don't need you to remember that particular number. It's about 2,000 times smaller. It's so small that in a lot of the calculations we can just pretend that it doesn't have any mass at all. So the protons and the neutrons are the ones that have mass, and the electrons essentially don't have any mass because they're so tiny. It's like if you had a big truck full of peaches and you threw, just loaded with peaches, right? And you threw a ping pong ball on top. Would that really matter in terms of the mass of the whole truck? Nope, wouldn't matter at all. That's how the electrons are. They do have mass, but compared to everything else in the atom, it just really doesn't matter at all. So the nucleus is very small in size, but it has 99.9% of the mass of the atom. What happened to my picture? My picture's gone. Hang on. Okay, I found my picture. So if the proton or the neutron, which are about the same size, if they were as big as a baseball, the electron would have the mass of a grain of rice. So that's just to give you some relative scale. So you think about a bunch of these in the nucleus, and then these electrons, little teeny tiny guys, their mass just really doesn't matter that much. This one's interesting too. So here's a picture of a football stadium. If the atom was the size of the whole football stadium, that's big, right? That's a big football stadium. The nucleus would be the size of a marble. So imagine the atom this big, and right down here in center field, that's baseball, on the 50-yard line is a marble. Not even a shooter marble, just a regular sized marble. That's the nucleus compared to the whole atom. There's a lot of empty space, right? Because if we're now making the nucleus be the size of a marble, that's a lot smaller than a baseball. And compared to a baseball, an electron was a grain of rice. So if we're making this out to be a marble in the middle, then we've got a few electrons in this huge volume, and they're way smaller than a grain of rice. So there's a lot of empty space. So it's no wonder that most of those particles went straight through the gold foil. But that nucleus down in the center is so dense that if you make a direct hit, it's just going to bounce something back. It's a little bit like, see, my sons play football, so I have an affection for football players. And when my son played at COS, there was a guy, I think he played on the D line. He was like 300 pounds. Actually, I think he was over 300. He was ginormous, okay? And then you think about a small child like Andrew, my son, who's 5. And you think about Andrew running full blast and running into this 300-pound lineman. Is Andrew going to move him at all? No. Andrew's going to bounce off, right? And that's what happens when one of those alpha particles hits that nucleus, because it is so massive. They just bounce off. So almost all the mass of the atom is in the nucleus. And because it's so tiny, it has to be incredibly dense, and it is. It's mind-bogglingly dense. Its density is on the order of 10 to the 13th to 10 to the 14th grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter. And you know how heavy even a bucket of water can get, right? That is fairly heavy stuff. Okay, this is a 1 with 14 zeros after it, the density. It's mind-boggling. Lead has a density of 11 grams per cubic centimeter. I think this one's even better, though. If you had a matchbox, a little matchbox, not the big kind, just a little kind, and it was full of nuclei, it would weigh over 2.5 billion tons in a matchbox. That boggles my mind. I hope it boggles your mind, too, because it's just hard to think about.